going to be working with this next worksheet 07, which is going to deal with some applications for first order differential equations. So just be aware, there is no class on Monday. You're welcome to come here. I don't think the Zoom room will be open. But if you do have questions on Monday, I'm happy to meet. If you want some office hours, that's totally fine. The homework for next week is due on Tuesday evening, and then you'll have a reading quiz for Wednesday's class. That's the plan for next week. But any questions before we get started today? Okay, so just I want to correct something that I misspoke about the start of last class. So at the start of last class, we were talking about the reading quiz for Monday, which was essentially trying to identify what type of differential equation you have. Is it linear? Is it separable? And the quiz was graded fine. I just made a mistake with this example over here. We said it was linear, and it is. I said it was not separable in when we started yesterday, when this actually is a separable differential equation. So I just want to make sure I correct that in case there was any misunderstanding. And so here you can see how it's separated. And so then just to quickly touch on the material from the reading quiz for today. So one of the problems asked you to integrate this. And I think some people might have missed the negative sign. So there were a couple of errors on this one. So just be sure that when you're integrating this, you would do a U substitution or W substitution on this, and that's why you get this leading negative sign in that integral. But any questions about that one? And then there was the partial fraction decomposition problem. So the context here was you wanted to say integrate something that looks like this. And when you're trying to integrate fractions and substitution doesn't work, then you might try and break it up. And so if you're having trouble, if I'm breaking up, please just chat and let me know. I just got a warning that my internet signal is weak. So we could break this up. That's what you were asked to do, and find values for A and B, which in this case were 4 and 6. And that seemed to go pretty well. And so I just want to kind of wrap it up with like, well, why would we do that? Is now we've taken this fraction that was in here, and we're able to write it as a sum of two fractions that look like this. And I can integrate each of these things. So for this one, we could write this as a times the integral of 1 over x plus 5 dx plus b times the integral of 1 over x minus 3 dx. And that's just saying if we were to substitute this decomposition in for the original fraction, then we can break up that sum. And now you would get a, which in this case was 4, times the integral of x plus 5, which would be this. And then we would get plus b, which is 6, times the integral of x minus 3, 1 over x minus 3, which would be that. So that's how that would finish up if we wanted to integrate that. Questions? Cortez?
Yeah, so I got 4 and 6 for my answers on the quiz, and then it said it was wrong.
I'll have to check on how maybe you entered them in the wrong spot. I'll have to double check that. I don't have it in front of me, so we can check it out after class if you want. Yeah, I think it was grading it properly, so it might have just been an issue of entering something in the wrong spot. I can take a look.
Okay, because it's in the same spots that you have there for 4 and 6, like A is 4 and B is 6.
Okay, like I said, without having it in front of me, I would have to open it up and take a look at it, and I don't want to do that in front of everybody, so that's something we can talk about privately. Yeah.
While watching your video, I learned how to solve partial fraction decomp a little differently.
Okay.
I multiplied them by like the quadratic in the bottom to the x plus 5 and x minus 3 by all of them. So I got a times x minus 3 and b times x plus 5 in our thing. And then I put in like different numbers for x and x to solve for a and b. I'm wondering if we have to use your like systems of equations kind of setup that I saw you were doing.
At the end of the day, those methods would be equivalent. You've got two things that you need to solve. So at some point, you should have two equations that you're going to need to solve in order to solve for those two unknowns. Yeah. So it might just be a different way of organizing the work, but at the end of the day, more or less, it's the same algebra. Yeah. So you're welcome to do it whatever way you feel most comfortable. Yep. Okay. Any other questions? Yeah, and that answer goes for anything. I mean, you're always welcome to solve things in whatever way makes the most sense to you. Okay, so for today, we're not going to take a look at any new types of methods of solving differential equations for today. And next week, I want to look at applications of these models. So I want to think about where do these models come, how do we set them up, and then how can we use these methods to solve applications. So the book, the notes on DiffEqs is a little bit light on applications. They do some mixture problems in the section where they talk about integrating factors. I put up some reading materials from another textbook that does application problems in a little bit more detail. So you can take a look at those reading materials to take a look at some applications. And so today, we're going to take a look at some population models and some mixture problems, and it's in those notes on applications. So here we're looking at chapter 4 of those notes, but I just kind of picked off the particular pages that apply to this. And first application is this salt solution sort of application that we looked at last class. So I want to revisit this and talk about how we can set up these models and then how we could solve them. So just recall that the idea here is we've got some sort of tank and there's water going, or some solution going in, and there's some solution coming out of this tank. And so what we're told is, let's just kind of highlight some of the important information here. So we're told that a brine solution that has a concentration of 0.05 kilograms per liter flows at a constant rate of 6 liters into the tank. So all of this information is summarizing the input rate in the tank. Then if we read on, we're told that initially the tank contains 50 liters of a 1% salt solution. So all of this stuff over here right? That's not telling me anything about the amount of solution that's going into the tank or the amount of solution going out of the tank. It's just telling us what is the state of the tank when things start flowing in and out. And now we've got some information about how it's flowing out of the tank at a rate of 4 liters per minute. We're going to have these three things. How's it flowing in? How's it flowing out? And what is the initial setup of the tank? And the way that we thought about setting this up last class was to think about these two models as two separate models that we can combine. We can model the rate at which salt is going into the tank. We can model the rate at which salt is going out of the tank, and then we can combine those two models. So just to do some scratch work, maybe I should keep my colors the same here. So for the input rate, just going to make some general notes. For these problems, that's always going to be let me just put it like this, the rate that water or solution is going in
be salt? Because that's the thing we're trying to find.
Sorry,
Or
we
solution.
had a guest here. What was your question, Abraham?
Would that be salt or solution going into the tank? Because we're trying to
Solution.
find the salt. Okay.
Yeah. And so ultimately what we want to see is the rate at which the salt is going in. That's right. And that's going to depend on two things. How fast is solution going in and what is the concentration of that solution? Yeah. So that would be the second part of this. And so these are values which should be given to you pretty explicitly in the problem. And in the end, what you're going to get is would be the rate that salt goes in.
Why is it rate solution flows out for the input rate?
Oh, sorry. Yeah, sorry. You're right.
Oh, okay.
Thanks. And it's similar for the output. That is, we would take a look at the rate that solution flows in. Excuse me, flows out. And then we would multiply that by the concentration of the solution flowing out. And again, when we multiply all of these things, we should get units that look like units of how we're measuring the salt per units of how we're measuring time. So it's always good to just do a check on your units when you're setting these up. And when you're coming up with these models, I'll just say pretty much everything is going to be constant except for the thing that I just highlighted in orange. Because the amount of salt and possibly the amount of volume in the tank is changing, the concentration flowing out is going to change, right? Because the concentration flowing out of the tank is going to equal the concentration of the solution that is in the tank at that time. So when we were reading this problem up here, right, we're given information about what is the concentration going in, what is the rate that it's going in. We're told the rate that the solution is flowing out, but what we're not told, so what we have to think about is what is the concentration of the solution flowing out. Okay, any questions? Okay, so then let's try and think about this. So in part A, we want to figure out, well, what is the input rate of salt into the tank? And so what is the rate that the solution is flowing in? You can chat it in if you like. I just want to make sure you guys are following along.
Should be 0.05 kilograms per liter going in.
That's the concentration, right? Yeah. So we're going to use the concentration and the rate that it's flowing in. So I guess you can do it in any order. But yeah, sorry.
6 liters per minute.
That's right. Yeah. So we've got the 6 liters per minute. And I think it is good to keep track of your units here. And then, yeah, then we've got the concentration, which was 0.05 kilograms per liter. And now you can check, multiplying these units, we would get something that looks like kilograms per minute, which is great. So the rate that salt is going into the tank is constant, right? Since the concentration isn't changing and the rate isn't changing. Any questions? And so, yeah, I think it's good to kind of keep in mind what's the general picture here. Like, what are we doing in this problem and how could we extend this in general to other sorts of problems like this? Okay, and then for the output rate, if we do a similar sort of thing, what's the rate of that the solution is flowing out of the tank?
Four liters per minute.
Yeah, so that's going to be 4 liters per minute. And now here's the tricky part, since this was kind of the one bit of information that's changing. This wasn't explicitly given to us, but what we should have here would be what is the concentration flowing out of the tank? So the way that we can think about this we could think about this as how much salt is in the tank divided by what is the volume overall of the solution in the tank. So we've got these 4 liters per minute. And then again, this is the part that's changing. So how could we express total for the amount of salt that's in the tank at time t?
Don't you have to like come up with a model for it based on what the outflow is? Like we did on the other problem from Monday?
Yeah, so we're coming up with a model for it, yeah. And so we want to come up with a model for the concentration that's in the tank at time t. And so this depends on 2 things. What is the amount of salt in the tank and what is the volume of the solution in the tank? Maybe let's start with the volume of the solution in the tank. So we start with 50 liters in the tank. It's going in at 6 liters per minute, coming out at 4 liters per minute. So what's happening to the volume in the tank as time goes on? Is it going to stay 50 liters? Is it going to be increasing or is it going to be decreasing?
It's going to increase.
Yeah, it's going to increase because we have more stuff going in than coming out. So how could we write a formula for this?
It'd be 50 plus 2. Yeah.
So this would tell me that the volume of the tank is going to be 52 liters always, right? And the volume should be changing a little bit, right? So this 52 would be what is the volume 1 minute later, but in general, we want to find the general formula for how is the volume changing with time. So does anyone see how we could fix this? We got some on the right track here.
You have 50 plus 2t.
Yeah, so what's happening is every minute the volume goes up by 2. So now we've got formula that's telling us how the volume of the tank is changing with time. And then how can we express the amount of salt in the tank? What's that called? That's X, right?
Yeah.
That's exactly what X is representing, the mass of salt in the tank in kilograms. So generally speaking, this concentration is always going to be whatever the variable is that you're representing the quantity, in this case, salt, divided by volume. So typically, the amount of salt in the tank, that is exactly X. And what happens is the volume typically depends on time t. So this volume that we had in the tank was a combination of what was the initial volume of the tank, and every minute, how much is the tank's volume going up or down. And this is going to be kind of the general, pardon the pun, the general flow of all these problems. Any questions? So if we were to combine then all of this, we would get that dx dt is equal to the rate that it's flowing in, which was the 0.3, minus the rate that it's flowing out. And there's our model for the rate of change of the amount of salt in the tank. So you definitely will have a homework question that's going to ask you to set up a similar looking model. And these reading materials have some examples, as well as section 1.4 of the notes on DiffyQs. And so the last thing that I would like to fill in with this problem is ultimately we would like to solve this, and we should get a unique solution here because we do have some initial conditions given to us. So it would be nice to just describe what those conditions are. So this x of 0, this is representing how much salt is in the tank at time 0. And now this is not saying concentration in the tank, but it's saying how much salt is in the tank, because x is representing the mass of the salt. And so if we've got 50 liters, 1% of that is salt. Right, that means we can take these 50 liters and multiply it by 0.1, that 1% kilograms per liter. So sometimes these concentrations are given as percentages that we just would then convert to a decimal. And that would give me 0.5 kilograms. So that would be my model. I've got my differential equation along with my initial amount of salt, which is, if it's 50 liters, 1% of it is salt. That means we have 0.5 kilograms at time 0. Okay, any questions? Okay, And then if we want to try and solve this differential equation, okay, first of all, it's first order. So we've talked about different types of first order differential equations. Could we separate this differential equation? Give me a thumbs up or a thumbs down. So I'm hoping to get some responses from you guys. If I'm not, I will start calling on people. So is this going to be separable or not separable? Okay, so what do you think,
It looks
Austin,
like-
about this one? Sorry, I can't see you, so I can feel free to chime in. Do you think this is separable or not? Are you there, Austin? Okay, how about Ben? What do you think? Is this separable or not separable? Are you there?
I don't think it is separable.
Okay, thank you. This is not separable, that's right. Thank you, Ben, because we have a difference on the left side, and there's no way that I can take that difference and write it as x, something that only depends on x times something that only depends on t. If we didn't have this there, that's a separable differential equation because it doesn't depend on t at all. But we do have that down there. So that means separation of variables wouldn't work on this one. However, this is linear. Since we have nothing that's being multiplied by the first derivative of x, and the stuff that we're multiplying by x, which is the 4 over 50 plus 2t, that is independent of x. So that is linear in x as well. So this equation is linear in the first derivative and linear in x. So this means if we want to solve this, then we would need to use the integrating factor. And kind of reverse engineer the product rule there. Okay, so any questions about how we set up this model for the tank? Okay, so then let's move on and check out some population models that we've been working with and see how we can refine these. So we can think about a population model similar to this mixture problem where the tank is now the world and the rate of inflow is the birth rate of the world. And so we've been talking about some models where the population, where we assume the population grows at a rate which is proportional to the current population. And those models look like this. And when we solve those models, they have exponential solutions. So when we are assuming this method, what we're assuming is our solutions look like this. So we don't have any kind of equilibrium sort of flattening out behavior. And if we use models like this, so if I use this model, so I constructed this model based on the population of the world in 1960 and the rate at which the world's population was growing in 1960. And that gives us this model over here. And if I use this model to make a prediction for what the world's population was at the end of 2019, I would get 9.76 billion. The world's population, I don't know exactly what it is. It's something close to like 7.5 billion. So we're off, right, by a lot here, by like 2 billion people. So what do you think is wrong with the way we set up this model as it stands?
Doesn't take into effect the negative population, people dying off.
Yeah, so this doesn't take into account anything leaving the tank, right? So all we've taken into account is the birth rate really here. And this is a perfectly fine model for the rate at which populations grow. It tends to grow at a rate which is proportional to the current population, right? The larger the population is, the more interactions you have, the more growth you're going to get. But the downside is that when you do get a large population, then there are things like, you know, competition for resources and disease and wars and all these other things that cause some decrease in the population. That's right. So for this model, we have not taken into account any death. So that's where we can refine this model. And when we do so, we're going to come up with something which is called the logistic model for population growth. And I'll just say that this model applies to other things as well. It applies to things like disease spread of technology, and other sorts of growth. So the birth rate, that's fine. We've got that as K times B. And so the question is, what's a reasonable model for the death rate? And so what this logistic model assumes is that the death rate is going to be proportional to the number of two-person interactions that you have throughout the world. Okay, and so the idea here is any two people have the potential not only to reproduce, but also to spread disease to each other, to compete for some limited resources. So you kind of think of it as, okay, someone's got to eat, and that means the other person is not. So that's the kind of depressing side of this model. So the way that we can represent that is we can think about how many different ways can we pick two people out of the entire world population. And so in combinatorics, we call this P choose two. And so I'm kind of getting sidetracked a little bit, but in case you're kind of curious, or if you've seen this in another class, that's the formula for how many ways out of n things could we pick k of them. And so if we did this for P choose 2, then technically we get P factorial over 2 factorial times P minus 2 factorial. And are you all familiar with that factorial notation? So that means like P times P minus 1 times P minus 2, etc. So we can get this cancellation of P factorial divided by P minus 2 factorial would just give us P times P minus 1. And on the bottom, we have 2. So that's where this part of the formula comes from. So if we take the same sort of approach for that we did with the tank and the solution flowing in, we have kind of the inflow of people, which we can write as some constant, I'll call it K1, times the current population. And then we want to take into account the outflow, which would be this K2 times P times P minus 1, all divided by 2. So these logistic models always look the same. The difference is going to be these constants K1 and K2, right? They're different for different species. Different species reproduce at different rates, and they also die out at different rates. So that might depend on you know, a number of different factors, but they're representing constants. And I'll just say that when we're working with these models, it is going to be really convenient to write them, to simplify this a little bit, into the following model, because if the model is presented in this way, we can see that we have equilibrium at p equals 0 and p equals L, right? Because those are the two values of p that make the PDT equal to 0. And so what we'll see here is that these populations don't grow infinitely large. They flatten out around this value L. So it's going to be useful to take this model that we have written up here and rearrange it so that it looks like this, because it's going to be easier to identify equilibrium in when it's written in this way, and it's also going to be easier to solve the differential equation when we write it like this. So just to go through the algebra, right? What I could do is take this term over here and write it as p squared minus p over 2. And then distribute this out. Okay, so I just distributed the p through the p minus 1, and then distributed the k2 through each of those terms, those two terms. And so now we can write this as just grouping my p terms together. And now it's just about in the form that we have above. And I could say then we could just factor out this minus k2 over 2 and p from each of those terms. And what we would get left with is some expression of p minus L left over. Okay, so this L, right, depends on k1 and k2.
So what would L equal in terms of K1 and K2?
It's going to equal, right, it would just equal minus k2 over 2. We would divide by that times the expression, right? Because all we did is we factored out minus k2 over 2. It's really not important how it depends on k1 and k2, actually. It's more important that we can identify it after we've written it in this form. So really what I'm trying to emphasize here is that we can take this model, which somehow takes into account separately how it's growing and it's decreasing, and we can rearrange the terms to put it in a form where we can very clearly identify what the equilibrium solutions are. So usually we don't worry about what K1 and K2 are. We try and identify what the values for A and L are. And we'll see this when we take a look at the practice example on the next page. So main point here is that when you have the Malthusian model, it looks like the PDT is equal to K times P. And when we're doing the logistic model, here's kind of the motivation about where this model comes from, but in the end, this is gonna look like this form over here. Sorry. And kind of what's the difference between these two models is one of them does not take into account any rate of decrease. And that's why you get really bad estimates in the long run with those. Okay, any questions? Okay, so now let's think about how we can solve these logistic models, since we've already solved the Malthusian model. So I wrote it out down here, and I just want to take you through this one time so that we can kind of see where the shortcut for solving these come from. But let me just say that this solution comes from doing partial fraction decomposition, which is why I wanted you to look over that in advance. So if we want to solve a system that looks like this, then the first thing that I can do is notice that this is separable because it doesn't depend on t at all. So I can divide both sides by 1 over p and 1 over p minus L. And that's what we have over here. Right, this step is just saying we're going to separate that differential equation, and then we're going to integrate both sides after we separate. So integrating the right side, that's not the issue. But integrating the left side, that's not as trivial. And so when we integrate this side over here, we would want to use this method of partial fraction decomposition. Again, I'm not going to go through this in huge detail, just because I don't think this is the best use of our time together. I'd like to try and solve some equations, but I do want to just show you where this shortcut comes from briefly. And so if you wanted to break this up using partial fraction decomposition, you could see, you could solve for A and B so that when you add these together, you get 1 in the numerator. And that means that this integral that we started with, we can write as A times 1 over P plus B times 1 over P minus L. And that allows us to integrate each of these things. So when I integrate this, I get the minus 1 over L times the natural log of absolute value of P. And when I integrate this one with respect to P, I get 1 over L times the natural log of P minus L. And here, technically, we should have absolute value. And then let me just say, skipping some of the algebra, at this stage, what we would like to do is solve for P. So I have this equation, 1 over L, and I can combine the natural logs using properties of natural logs. And all of this step over here is the process of solving for P, because in the end, we would like to have our solution in an explicit form. P is equal to some function of T. And this is the main point here, is that we can solve this using separation and partial fraction decomposition And we can get a general solution that is always going to look like this. So what we can see is in this solution, we have L, which is a constant. We have A is a constant. Okay, not arbitrary constants, but they are constants that we identify in the original model. And then we have C, which is gonna depend on our initial condition. So when you're solving these logistic models, I would kind of recommend that you're familiar with where this formula comes from, but you're welcome to use this shortcut for expressing the solution. You don't have to go through the partial fraction decomposition every single time.
I have a question on
Sure.
the derivation of that. When you get to the part where it's like natural log of absolute value of P plus natural log of absolute value of P minus L,
Mhm.
you're just like pulling out a -1. So then when you rewrite that, it's a quotient and not a product, right? Is that how you end up getting that? Because like if you factored out 1 over L, it would just be P times P minus L, the natural log of that. So you factor out the -1 so you can make it into a quotient.
So if you factor out, I'm just factoring out 1 over L. And when I do that,
Okay.
what's left over is this. Right, so we have the negative from this one over here. And now to go from here over to here, we're just using the property that when you're subtracting two natural logs, it's like taking the natural log of their quotient.
Okay.
Yeah, so the natural log of P over L minus the natural log of P is the same thing as the natural log of P minus L over P.
Okay.
Yep.
In that term, where the exponential is in the bottom, it's C times E raised to the -A. And is that an L or a C?
No. So
Thank you.
Yep, that's an L and an L and an L. Okay. Any other questions?
Could you just clarify, if you scroll up, where did you, when you set up the integrals, I'm having trouble finding where you got 1 over P and then multiplied it by 1 over P times L. I feel like I'm just missing something simple.
Yeah, if you separate this, so you have dp dt is equal to minus A times 1 over P, or excuse me, times P times P minus L. So we divide by P, and then we divide by P minus L to bring the P's over there, and then over here
I see.
bring the dt over there.
Okay. Yeah, thank you.
Yep. Yeah, I think it's one of these things that you have to go through on your own, honestly, and try and read it. I don't think that is the best use to kind of go through this all together right now. But if you have some questions about this, I'm happy to stick around afterwards. I would just like to kind of say, let's see how we use this result now to actually solve some problems. So let's take a look at this model over here. So this would be an example of logistic growth for this population. So if we're going to try and use that shortcut, we want to factor this and try and put it in the form where we've got this like that, right? Because we need to identify what A and L are in order to use that shortcut that we've been talking about. So I'll leave it for you to take a second and just try and factor this. And then identify what are the values for A and L in this model. And then when you've got it, I would like you guys to chat it in since, yeah, I don't want to have to call everybody out, but I do want to give you all a chance to respond just so I know what we need to spend more time on or not. So, just let me know what it is and you're welcome to just chat it to me privately in the meantime. And so just so you know, like in this model, P is variable. So you should be getting that A is equal to a constant number and L is equal to a constant number, and it shouldn't depend on P. Yeah, so just be sure that when you're saying A, it's just the value of A and not including the P. Okay, so I'm just looking at the answers coming in, looking good. But yeah, this is why it's helpful to see these things come in because yes, there are some mistakes that a number of you might be making. So I just want to make sure I catch them while we're together. Okay, so here was our initial differential equation. That's right. And so what we're hoping to do is use this shortcut that we have over here. Okay, so that was the shortcut that we want to use, okay? And so notice, like, really all we need to identify to get this general solution are what is L, what is A, and then that value C is going to depend on the initial condition. Okay, yeah, so to write this in our kind of standard form for the logistic model, I can factor out a P from both terms. And then what I'd like to do again is have this in the form of minus AP times P minus L. So that means, notice that when I write it in this form, the coefficient in front of P should be 1. And so if I have a coefficient of minus 1/20th, then I just want to factor that minus 1/20th out. So when I do that, that 3 becomes minus 60 when I pull out minus 1/20, and that makes the coefficient in front of the L equal to 1. Whoops, that's a P over here. So that's what the model would look like when we put it in the kind of standard form that we can use our shortcut to find the solution. So here we've got that A is 1/20 and L is 60.
Professor, I was one of those that goofed and put A as 20. Was that a common mistake?
I would say, I don't know, with I don't know. I mean, what's common? This doesn't matter if lots of people make it or none. Yeah, I'll say, you know, people were mostly getting 1/20 and some variation. The variation, I didn't see any common pattern in that. Any questions about where we found those values from? And great, so then this tells us, okay, this is gonna go here, 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 there, and this value for A, right, that's gonna go right there. And that's gonna be enough for us to find our solution. Right, so this would be P is equal to, we had L was 60. We had A was 1/20. And we had L again was 60. And so that's our general solution. And then we would want to use our initial condition to figure out what is the value for that arbitrary constant C. And that we can see depends on our initial value P0, but it's not directly the initial value. We get that from this formula over here. And in this case, our P0 was 50. And simplifying that would give us 0.2. So there we've got our particular solution to this initial value problem. We didn't actually integrate anything to solve this. We kind of used the fact that we did integrate in the general case to come up with a general form for these solutions. So when you're doing this on homework, you're welcome to solve it using partial fraction decomposition, etc. You're welcome to use this shortcut. If you do use the shortcut, that's what I would recommend. Just be sure you show some work, like how did you figure out what A and L are, and that's sufficient. Right, questions?
Is this something we use, I guess, what is the advantage of using this over partial fractions? Or is this something you use when you can't do partial fractions?
You would do this using partial fraction decomposition. So you can either do partial fraction decomposition every single time, but that formula came from us just treating the most general case without worrying specifically what A and L are. We're able to use partial fraction decomposition to find the general form for the solution. So this formula that we got used partial fraction decomposition. So you can either do this every single time, plugging in the values for A and L and solving it, or you can use the fact that we've done that for the most general case, and now we can apply this to any logistic model once we know what A and L are.
Okay.
Yeah, so they're not different methods. One is, this was derived using partial fraction decomposition.
If we aren't given P of 0, you'll always give us a C value, right? So that we can calculate P of 0?
You would have to know, it usually goes the other way. Like you would have to know what P0 is in order to figure out what C is. Yeah.
Okay, when would we use the P of 0 equals 1 over 1 plus C then?
You probably wouldn't, and that's why I took this equation and rearranged it to solve for C, because usually you know what
gotcha.
P0 is and you want to figure out what C is. Yeah.
Gotcha.
Okay, so here we found the explicit solution to this differential equation. So now I can say, okay, if I know that our population started with 50, I want to know what is the population at any point in time, right? This model would be helpful for that. Oftentimes when we're working with things, what we really are interested in is what is the long-term behavior of our solutions? So for example, what happens to P as time goes on? And so as T gets infinitely large, let's just kind of think about what's going on with this term over here. So if I'm plugging in something really, really large for T into 0.2 e to the minus 3t, what's going to happen to the thing that I circled in blue?
It's gonna
Approaches 0.
approach 0, yeah.
Yeah, so we've got e to a negative power. That's right. So as t gets large, this thing is going to head to 0. So as t goes to infinity, what we actually get is 60 over 1 plus something which is heading to 0. So we can see here that as time goes on, if we start with 50 rabbits, as time goes on, the population is not going to grow infinitely large. It's going to flatten out at 60 rabbits.
Hey, 60 is L in the equation. So would L represent the carrying capacity of a environment?
Yeah, that's right. So the reason why it's useful to write it like this, factored out, is because this helps us identify exactly what are the equilibrium. That's right. And so we can see from this factor, we have one equilibrium at 0, and we have a second equilibrium, P is equal to 60. And then you can think about whether these things are stable or unstable using the phase line analysis that we looked at a week or so ago. Yeah, so it's not surprising. I do want to connect the behavior of the explicit solution to the analysis that we were doing with phase lines, because they're not going to give us different answers. So this solution is not going to, blow up exponentially. It starts to increase exponentially, but then what's happening is it should start to flatten out at this equilibrium population. Okay, any questions? Okay, so let's think about these questions over here. So this is actually a review of stuff that we looked at earlier with equilibrium, stability, phase lines, that sort of stuff. So all of these questions here are really just asking us about what does the phase line look like. And remember, we can use the phase line when we are dealing with autonomous differential equations, which this one is, because this one does not depend on time. So just kind of recall that for these sorts of problems, how we went about this is we identify our equilibrium by identifying what values of P make the differential equation equal to 0. Okay, again, we've got 2 of them for this problem, 0 and 60. Then we kind of sketch our line and mark our equilibrium on that line. So I'll do it over here. And then we pick a test point in between each equilibrium. And what we're interested in is finding the sign of the derivative to know whether my solutions are increasing or decreasing. And I'll just say, just kind of quickly checking that if you plug in some values between 0 and 60, you get the PDT is positive. If you pick value bigger than 60, you'll see that the derivative is negative. And if you pick a negative value for the population, just to get an idea of what the dynamics look like, you would get that that is also negative. So we see that this P equals 60 would be a stable equilibrium. P equals 0 is unstable. And so like question A is just saying for what initial populations does the population grow at first? And this is going to be essentially for what values of P is the derivative positive at first. And that is that portion right there. Okay, so for any initial population between 0 and 60, that population is going to grow but not infinitely. It's going to grow, but flatten out as it approaches 60. And then for the others, we've got two regions for that. And this region down here and this region over here, the derivatives are negative. Let me just say, this consideration of a population being negative, we don't need to really think about here in this context of populations. So what we can see is no matter what, if we start with more than 60 rabbits, as time goes on, that population is going to decrease, but approach this stable quantity of 60. And if we start with a population below 60, that is going to increase, but it's going to flatten out as it approaches this stable equilibrium. So this value, this stable equilibrium that was exactly just equal to the value of L in our model, notice, is what's called the carrying capacity. Okay, meaning like this is the maximum population that this ecosystem can sustain. And that's oftentimes good to know. What's going to happen way out into the distance. So it makes sense that if you start with a population which is too large, there's going to be competition, limited resources, and that population is going to decrease. But if you start with a population which is sparser, there's not as much competition, makes sense that it's going to grow at first until competition sets in. Yeah, and hopefully it makes sense that 0 is a very unstable equilibrium, because once you introduce 2 rabbits into the population, they multiply. It's not going to head back to 0. It's going to head off and the population would increase. Okay, so I will stop here for today. We can pick up with this problem next time. So y'all are welcome to go about your days. Have a nice day. If you want to do a practice problem with using the integrating factor, I'll hang on the line. I've got an example that I'm happy to work through. So if you have questions about that and you want to stick around, feel free. I will record it, put it up online if you can't stick around. So, okay, have a nice afternoon, everybody, and have a nice Labor Day weekend if I don't see you.
Hey, Adam.
Yep.
Can we talk about the quiz?
Yeah, let me just kind of see what, if people want to go through this example together first.
Okay.
And looking at your quiz is something we can do together. I just don't want to do it while other people are on the line. Something we can probably, I can just take a look and send you an email as well to see why that happened.
That's fine.
Yeah.
All right. Cool. See you later.
Yep. Okay, so let's see. Here's the example that I had in mind to work on. Yeah. Okay, so let's say we want to solve this, and let's even throw in an initial condition. We've got this initial value problem. This is actually, sorry, this is not a linear differential equation. This is a separable differential equation. Yeah. Let's change it to this. Okay, now it is linear, and now I don't know what the solution will look like. So let's solve this one, and actually let's just find the general solution for this. You don't need to worry about the initial condition. Yeah, so I guess like first thing to think about is, yeah, this thing is linear because if I distribute that, and it is also separable, so let me just say you could solve this using separation of variables as well, and you might want to think about comparing those two methods, but this is linear, and I can kind of bring my terms to the other side and then put it into standard form. So kind of on the general step that we're doing here, putting that into standard form, first of all.
Isn't it 2 cosine x and negative 2 cosine x?
We multiply everything by 2, not divide everything by 2. Yeah, thanks. Let me just rewrite that. Thanks. Okay. And so our p of x then is this minus 2 cosine x. We do need that negative sign there. Yeah, so then next would be find the integrating factor. Right, which in general we find by e raised to the integral of p of x. And so for this one, we would get that our integrating factor mu is e raised to the integral of minus 2 cosine x dx right, which give us e to the minus 2 sine x, right? When we integrate cosine, we get sine. And I don't need to worry about any sort of plus c at this point in the process. And just feel free to yell out if you've got a question. Then we take our differential equation that we had over here, and we're going to multiply both sides of that differential equation by the integrating factor. And let's see. So that would mean we've got y prime times e to the minus 2 sine x. Minus 2 cosine x times e to the minus 2 sine x y is equal to minus 2 cosine x times e to the minus 2 sine x. Okay, any questions? Okay, all I did right was just say we're going to multiply by this integrating factor And we need to do it to every single one of these terms, all three of them. So that's where this term comes from. Okay, so now that we've done that, if we've done it correctly, we should be able to rewrite the left side as a product rule. Okay, and that integrating factor, if we did it correctly, should make this look like y times mu to prime. And it's not a bad idea to just check that if you were to take this derivative, yeah, we actually would get back the left side of the previous problem. So all of this stuff over here is like the derivative of the second function there that you would get using chain rule on that. Okay, and then once you've done this, then you can integrate both sides and solve for y. So the whole point of that integrating factor is now that makes the left side a perfect derivative. So the integral undoes that. And then what's left is to integrate the right side of that differential equation. And here's where it was dangerous because I just made this up off the top of my head, but I think we actually can integrate this, which is good. How could we integrate the right side?
You do U substitution?
Yeah, this seems like a good candidate since like when we take, there's some relation between the power inside the E and the derivative of that power matching up with the constant or the multiple in front. Yeah, so let's try like W is equal to -2 sine X. And then dW is -2 cosine X dx, and that's perfect, right? So that would give us e to the -2 sine X. And then lastly, what's left is to just solve for y by dividing both sides by e to the -2 sine X. So I actually get a 1 here. And I can just say, if we were to divide by -2 sine X, it's the same thing as multiplying by e to the 2 sine X. So this would be our general solution over here. And I don't think it's necessarily a bad idea to compare what would happen if you tried to solve this using separation of variables, which you could also do. We could have separated that from the get-go and just kind of compare how those processes work. Sometimes integrating factor is easier, sometimes separation is easier. But it's nice in cases like this that you do have different methods available to you. That's not always the case. Okay, so if there are questions about this or anything else, just let me know.
For the, you know how we just derived like L and A? When we do our homework, we just do L equals that, A equals that, and then just
Yeah.
instead of
Yeah.
okay.
So just to go all the way back over here where we did this, yeah. If you were trying to solve a problem like this, what I circled in green over here would pretty much be the work that you would need to show. So you have this differential equation. It's not evident, at least initially, what A and L are, but once I factor it and write it in this form over here, then we can identify what A and L are. Yeah, or at least this form over here. Yep, so that's totally fine. You can just show how you found A, how you found L, and then plug them into the general form of the solution.
Okay, thank you.
Yep.
Can you do
Thank
that
you.
like 6B from the homework? Homework 2?
Yeah, what was your question, Shamix? Oh, lost. I think he was heading out. Okay. So happy to do that, Brian. Just before I flip over to the homework, any other questions about this? Okay, so go ahead, Brian. So you said you had a question about homework 6, homework question 6B.
Yeah, homework 2.
This was homework 2 or homework 3?
Homework 2. The last one.
Last one, okay. Yes,
So yeah, just like what to do with that one would be the question.
Yeah, so for that one, you would need to use trig substitution on that. Let me just come to, so the original equation was y times dz dy is equal to 1 plus z squared to the 3 halves. So this is separable, so that's kind of the first step. So we could separate it out. And then the idea here is, right, I don't think integrating that side is the issue. But it's probably what to do with this 1 over 1 plus z squared to the 3 halves.
Yep.
Yeah, so let me just rewrite it. Like that. So saying 1 plus z squared to the 3 halves is the same thing as saying the square root raised to the 3rd power. Yeah?
Yeah.
Okay. Yeah, and so now whenever you see things like trying to integrate like something that looks like a squared plus b squared or a squared minus b squared, or things that look like this where you see lots of squared sorts of behaviors, and it brings up a picture of a triangle, a right triangle where Pythagorean theorem might be at play. So you can set up a trig substitution for this. And here's the reason why that might be useful. I see I've got like a square root of 1 plus z squared, and I can see that typically relates the two sides of a right triangle to the length of the hypotenuse. So if I set a equal to 1, b equal to z, then the hypotenuse would be exactly the square root of a squared plus b squared. And so now the idea is, well, how can we write like 1 over 1 plus z squared and dz in terms of trig functions and this triangle and this angle theta. So I can see that if I were to take, say, the cosine of theta, right, that is the adjacent side over the hypotenuse. The adjacent side is 1, and the hypotenuse is 1 plus z squared. So I've got 1 over the square root of 1 plus z squared is actually the cosine of the angle theta in this triangle.
Whoa.
Yeah, so this is a method of integration called using trig substitution. Yeah, it's one of the trickier methods of integration, I would agree. But there are materials, I think I posted materials in the integration review about trig substitution. But let me double check. I can put some materials there if I didn't put them up already. But to finish this one up, just because I need to go in a few minutes, but so the kind of key is setting up this triangle over here, which really unlocks all of these identities. And so looking at the ratio of adjacent to hypotenuse, that gives me exactly something really close to the thing I'm trying to integrate. So that original integral, I could just replace the 1 over the square root of 1 plus z squared with cosine. So this whole thing over here could be replaced with cosine cubed dz, but we also want to substitute out the dz in terms of theta. So I could use the fact that the tangent of theta is the opposite side over the adjacent side, which gives me just z over 1. So now I've got this identity that the tangent of theta is equal to z. So taking the derivative of both sides gives me a way of replacing dz with some expression of thetas.
Whoa.
And after I replace dz with its equivalent in terms of theta, when I take cosine cubed and multiply by secant squared, we get a bunch of cancellations, and all that's left is 1 power of cosine left. Which gives me sine of theta plus c. And then just the very last thing that we would want to do is we would want to express our final answer, not in terms of theta, but in terms of the original variable, which was z. And so I can use this relationship as well to say that theta is equal to the inverse tangent of z. And that's going to allow me to then finally write this as sine of the inverse tan of z. You get some really crazy looking solution like this in the end.